I'm Dave Spencer with VT Skated by Trihedral. We're here at the Launch Canada Challenge, talking to different universities and different teams competing to win prizes in various categories in rocketry here in Canada. Let's learn about some of the rockets that are here on site and see what the teams have to say.
All right, yes, so we are STARR, the Student Team of Alberta Rocketry Research, and our payload is called Biome 3. So that stands for the Bioaerosol Investigation of Microbial Ecosystems. We really just wanted it to say biome because it sounds cool. So basically the way our payload works is we have our structure here, and inside of it there's this air inlet hole right there. And so at apogee we are fully deployed out of the rocket. And as we fall to the ground, separate from the rocket, we have air that comes in through that hole and then enters a little sample chamber like this one here that sits inside of our payload. And inside that sample chamber, we've got tubes. And in these tubes, there is filter paper that are set into various slots. And as the air travels through that filter paper, bacteria from the troposphere is collected. And then when we come back to the ground, we can take that filter paper out, stick it in Petri dishes, let that cultivate for a couple weeks. And then after that, we can actually look and see what sort of bacteria that we've collected. So concentration, types, all that kind of stuff. And then also with that, we've got a grid fin system on our payloads. These grid fins are used to control our spin as we fall down. Because of the way our airflow system works, we just want a really stable descent, and so the grid fins are there to control that spin as we come down. So, yeah.
Cool. And you also need the rocket to go up.
Yes.
So this is another part of the project.
Yes.
So I wish you luck. What day are you planning to launch?
I think the goal is Tuesday right now, but we'll see how things go. So.
Okay, well, we'll hope to see you there.
Thank you.
All right, thanks very much.
You too.
Next up, let's check out UBC and see what they've got going on with their rocket.
Hello, this is our rocket this year, Sunburst. She's a single-stage rocket going to go about 15,000 feet. We have our nose cone here made of fiberglass, and she's very nice sunset color to match Sunburst. The whole thing is made with fiberglass except for the motor section, which is carbon fiber for weight savings. Yeah, we have some cool stuff in this rocket though. She looks pretty simple, but the internals are pretty cool. We have a lot of SRAD avionics components that are going to be on the rocket just to collect data, and our eventual goal is to try to use them as actual flight computers. And we also have a very cool payload testing microtubule dynamics. Oh, here. Yes, very cool payload. Shows in the nose cone. Yeah, we hope to launch tomorrow. We'll see how that goes, but we're feeling pretty prepared, so yeah.
And can you tell everybody what SRAD stands for?
Oh yes, SRAD is Student Research and Develop. So we made the computer boards for the rocket. Normally you're supposed to use purchase ones, but if you can develop one and test it and it works in flight, then you can use it as a board in competition. So that's our goal, is to test it and then hopefully use it for next year's competition.
Great, thanks, and hopefully we'll follow up with a video of that launch. All right, I've got Michelle with me, who's one of the judges for the competition here. Michelle, what is it that you'll actually be judging at this year's competition?
This year I'm judging the multi-stage rockets, 3 of them, and they are solid rockets similar to this one, but they'll have a booster and they'll have a sustainer stage. One is going to be flying to over 70,000 feet.
Wow, so what are the kinds of criteria that you're looking for when you're doing your judging?
We go and do the poster sessions here. We talk to the teams, we look at the setup, and we see that they meet the requirements of the competition as well as their own documentation, that they've done what they said they're going to do. And then during the week coming up, Monday through Friday, we're going to be following their progress assembling on site, preparing, getting ready, the integration, and getting to the rail and flying. So we'll be actually judging their performance in preparation and their performance in the flight and recovery as well. So recovery is a big deal out here in Timmins. We want the teams to go get their rockets after they fly. We want them to come back safely and with their rockets intact. And it's pretty deep forest out there, so that's part of the challenge here. And so we don't judge them on how well they do in the forest, but we do judge them on how well the rocket comes back in one piece. Or in the case of the multi-stage, two pieces.
Great, and how many rockets will be actually launching at this year's event, do you expect?
I think we have 30 of the high-powered rockets, approximately 30 teams here today. But then there's going to be hundreds of mid and low-power launches, and even hundreds of the children launching their small rockets like we used to fly when we were kids. So there's going to be hundreds of flights this week.
That sounds great. I'm looking forward to it. Thanks very much.
You're welcome.
Next up, we'll be speaking with the McGill team.
So we're going to start at the nose cone here. As you see, we've painted it black. So the nose cone is really important because it gives a nice aerodynamic entrance to the rocket. Over here, you cannot see the inside, but we have parachutes that are packed. And basically, we have an ejection system that will shoot the nose cone out of the rocket. And when it does that, the parachute will come out and the rocket will start going down, but slowly. Over here, we have our avionics bay. It is mainly responsible to actuate valves, which I will talk about later. It also collects data like, the GPS and location and everything like that. Then we have our payload. It's where the experiment happens. And our experiment has to do with bones and screws. So we basically screwed screws into bones, and we have different kind of pastes, and we test the effects of the rocket forces on the screws. Here we have what we call the vent section, and it is mainly responsible for venting the tank when we're filling. What that means is we need some sort of pressure difference when we're filling the tank from the bottom, so we have the vents open to allow venting outside. Here we have our oxidizer tank. It is filled with nitrous, and it is used in our hybrid motor, which I will get to soon. As you can see, there's plumbing that comes down from the tank, and here we have the main oxidizer valve, which allows the oxidizer from the tank to flow into the combustion chamber. We have a fill disconnect valve over here, which is responsible for filling the tank and also dumping out if we have to in case of emergencies. We also have a lot of other plumbing, such as pressure transducers and temperature sensors. Going down over here, we have our magnificent fin tube with fins on it. If you're familiar with fins, they're really important for the stability of the rocket, and they ensure that the rocket goes in a nice trajectory and doesn't just go ballistic. In our fin tube, we have our combustion chamber where we have fuel and we have an igniter. And the igniter basically starts the reaction and allows the oxidizer to react with the fuel to create thrust. And that's our rocket.
So my name is Justin from McGill Rocket Team. We're launching Project Power on Door this year. I'm working on the recovery, so we have the nose cone of the rocket, which is actually a bit back there, you can see. So everything starts at the nose cone. We have this little plate here that works as an ejection system. So it separates the nose cone, which is empty, and the recovery system, the recovery chamber. We have black powder that goes into these cups, and then we have E-matches that are actuated by the electronics. It explodes, basically, the nose cone pops off. It gets tension into the lines unfold, and then it releases the drogue parachute. Drogue parachute is a 48 inches parachute. It is fully SRAD, so it's student made and developed. We actually sewed everything that's in this parachute right now. Once the drogue is released, speed should go down up into 71 feet per second. After we reach 1,500 feet, we have main parachute release. To do that, we use a system which we call the tree rings. It's actually a system that's used in rigging to separate from your parachute from your back. So it works with an electrical actuator, so we don't have to separate the rocket again. We don't have to use pyrotechnics. So we actuate it's a little actuator here. It retracts, and then it releases a line here, which releases everything, and it separates completely. So we do have two of these systems for the redundancy, and they're plugged in two different places in the rocket. Once this release, another line gets into tension. This line is dragged by the drogue parachute force, and it releases our main parachute, which is 120 inches large diameter. This one is bought, but we did actually develop a main parachute that we will probably be using next year or in the years after, or even just as a testing device. And that's basically it. Once we're under main, we should reduce the speed up until 20 feet per second to have a good recovery on the ground.
Great, thanks very much.
You're welcome. Thank you.
Next up, we've got the University of Ottawa to tell us about how they're tracking data and bringing it back to ground.
Yeah, so this is the antenna tracker. So right now we have it connected to the Xbox controller, so we can control pitch and yaw. There's speed limiters to keep it nice and safe for the demo, but in flight we have it automatically tracking using the rocket. It sends down its GPS, and we do a bit of math, and then we point the antenna tracker. So right now, just quick demo, drive around. I can change the speed a bit and, make it go a little faster, but basically it works off a pitch motor and a yaw motor, both servos that we control through a Raspberry Pi compute module. And then we have our nice coder, Fernando, did a bunch of all the algorithm modeling, and then who does our nice GPS math. But yeah, we'll hopefully test it out tomorrow, and then nominal usage, we should be able to track the rocket and successfully recover through good, accurate GPS data.
Cool, and what kind of antennas are you using for this?
Way too overbuilt ones, I can tell you that. They don't need to be this big. They made it harder. The exact model's not off the top of my head, but it's at this point more of a show, kind of like, looking like a SAM turret out here, but yeah.
Right, that's very cool. And so, if I get it right, you're feeding the data from the rocket, including GPS data, back through to your control system that then tells the antenna how to aim to reach the rocket.
Yep, with the angular acceleration we need to input, we can send the motors, and then it continuously feeds back into the loop. We have two options. We can control using our SRAD computer, or we can have the onboard commercial featherweight system. Right now, we're still working out the kinks on our own student design system, so the featherweight commercial system is likely what will be used for tracking, but they'll still be receiving on both ends.
Cool. So the lag of time between receiving the data and moving the antenna must be critical, because if you have too much time there, the rocket, in theory, will fly out of its telemetry.
Yeah. So that is an issue. Good thing, these motors are very overbuilt, so they can pitch. These are significantly limited on an amp limiter, but these can pitch quite fast, like quarter of a second from fully down to fully up. Just in safety mode, we don't have that out. So even if we do have a lag, we should be able to speed up enough to the next packet that we receive, do the math, and then pitch up. We should, and since it is radar, we don't need, or not radar, but it is radio, we don't need to point exactly. We will get good data if we're in the general direction. So hopefully, we're not too much the speed of light limited, but I guess we'll see tomorrow.
So thanks very much for all that information, and good luck. When are you planning to launch?
Tomorrow, hopefully in the morning, depending on the weather, obviously, cloud cover and wind. We're high altitude, but 9 a.m., let's go.
Okay, well, hopefully see you tomorrow.
Yeah, there we go.
Thank you.
3, 2, 1, launch. We have smoke. Good time.